Hello everyone, today we are going to talk about short-term Fourier transform and analysis window. We assume you already know about DFT, and after this video, we expect you will know about what is STFT and get an intuitive sense of it. Also, you will know about the properties of analysis window and how to calculate the window length. Since the sound changes within time, it cannot be represented by a single spectrum. Short-term Fourier transform is able to deal with the time variation. This is the mathematical equation of STFT. Basically, it is a modified version of DFT, with a few but important differences. As you can see, the input signal is not just the x of n, but is the multiplication of w, which is our analysis window, by a fragment of x of n. And x has also a frame number and the hop size. L is the frame number, h is hop size. So we'll be iterating over L, skipping over time in this way. This is illustration for blocking signal with windows. The bottom one is the original signal. The upper ones are each block with being applied a window. As shown in previous figures, by applying window, we can reconstruct the same signal back when using overlap and add. Meanwhile, applying window can also smooth the signal between each block. We can analyze the window in both frequency and time domain. Firstly, let's look at it in frequency domain. The plot is typical magnitude spectrogram of a window function. This is the main lobe. These are side lobes. Main lobe width is the bandwidth of main lobe. The side lobe level is the difference between magnitude of a main lobe and the highest side lobe. The main lobe width influences the frequency resolution. The side lobe level affects the spectral leakage. Different windows have a trade-off between main lobe width and the side lobe level. Next, we will introduce some common windows. You should pay attention to the main lobe width and side lobe level of each windows. For instance, the main lobe width of rectangular window is 2 bins and side lobe level is minus 13.3 dB. Next one is Hamming window, and Blackman window. Okay, let's move to the time domain to analyze windows. Window lengths determine the time and the frequency resolution of the spectrogram. For instance, given a 20-second signal contains 4 frequency components. Each frequency lasts 5 seconds and does not overlap at all. So the ideal spectrogram is 4 clear segments. The first plot is spectrogram of the sun using 125 milliseconds long window. In this plot, we cannot really tell what the exact frequency, but we can see the clear and sharp boundary between each segment. Next one is the spectrogram of the same signal using 1000 milliseconds long window. In this plot, we can almost tell the frequency, while it's well blurry and at the boundaries. In general, the longer the window is, the higher the frequency resolution, the lower the time resolution is. At last, we will talk about how to calculate the window length. In this equation, Bs is the main lobe width, Fs is the sampling rate, delta is the frequency resolution, and m is the window length.